Tonight, when you check the time on your phone, you will trust that those glowing numbers are telling you something simple. You will think they are just measuring how late it is. You will assume time is straight, steady, and the same for everyone. But the real story behind those numbers is far stranger. You grow up feeling that time flows like a river, always moving forward at the same pace, carrying you from morning to night, from childhood to whatever comes next. It feels obvious. It feels unquestionable. And for most of human history, your ancestors agreed. Time was the background, not the main character. Why would you ever doubt it? Then you meet a patent clerk in Bern in the early years of the 20th century. You know his name already, Albert Einstein. You are told he is the one who shattered your comfortable idea of time. Special relativity, general relativity, the bending of spacetime. You might think he always knew exactly where he was going. But the truth is messier. The truth is that one of his biggest mistakes helped build modern time travel theory. To understand that wrong turn, you first need to feel the shock of his first right turn. In 1905, Einstein suggested something radical, that the speed of light is the same for every observer, no matter how fast you move. From that one stubborn idea, everything you thought you knew about time begins to crack. If the speed of light refuses to budge, then something else has to give. What gives is your sense of time. Physicist Hermann Minkowski, Einstein's former math teacher, looks at Einstein's equations and sees something even deeper. He tells you that space and time are not separate. They blend into a single four-dimensional fabric called spacetime. You are no longer just moving through space. You are tracing a path through time as well, a world line that marks your entire life as a single curve. Suddenly, time feels less like a river and more like a landscape. This is where the seeds of time travel are planted. If time is part of a landscape, then in principle you might walk around in it. You might imagine paths that loop, twist, or bend back on themselves. In special relativity, you already see time slow down for fast-moving objects. You learn the phrase time dilation, which simply means that for something moving very fast or sitting in a strong gravitational field, time ticks more slowly than it does for you. This is not just a theory. In 1971, physicists Joseph Hafele and Richard Keating fly atomic clocks around the world on commercial airplanes. When they compare those clocks to identical ones left on the ground, the flying clocks have lost tiny slivers of time. They have literally aged less. Your everyday world hides this effect because you move too slowly, but the universe does not forget. Time is flexible. It bends. It stretches. So where is the mistake? Where is the wrong turn that somehow pushes you even closer to modern ideas of time travel? For that, you travel with Einstein into cosmology, the study of the entire universe. After general relativity in 1915, Einstein has a new equation that describes how mass and energy shape spacetime. He expects to use it to describe the cosmos itself. But when he applies his equation to the universe, he runs into a problem. Gravity, in his theory, wants to pull everything together. A static universe, one that just hangs there and does not expand or contract, seems impossible. Under gravity alone, the universe should either collapse inward or expand outward. Einstein does not like either option. He wants a calm, eternal cosmos, not one that evolves. So he makes a choice. He changes his own equation. He adds a new term called the cosmological constant. It is like an anti-gravity factor built directly into the fabric of spacetime. If tuned just right, it can perfectly balance gravity and hold the universe still. Einstein is satisfied. For a while you are too. Then in the 1920s, astronomer Edwin Hubble measures light from distant galaxies. He discovers that their light is stretched, shifted toward the red, in a way that means the galaxies are rushing away from you. Everywhere you look, space itself seems to be expanding. The universe is not static. It is growing. Einstein hears this and realizes what his equation had been trying to tell him all along. He later calls the cosmological constant his biggest blunder. The story is usually told as if that is the end of it. Einstein made a mistake. The universe expands. You move on. But the cosmological constant does not disappear so easily. It lingers in the equations like a stubborn ghost. It will come back as something you now call dark energy, the mysterious pressure that seems to accelerate the expansion of the universe. And in between, it opens a strange door. That door is time travel. Not in the cheap movie sense, where you hop into a shiny machine and instantly change history, but in the precise, mathematical sense where the geometry of spacetime allows paths that loop back into their own past. Physicists call these paths closed timelike curves. A timelike curve is just the path a massive object like you can follow through spacetime. Closed means it loops. Here, another mind steps onto the stage, mathematician and logician Kurt Godel. Godel admires Einstein deeply. In 1949, as a kind of gift for Einstein's 70th birthday, Godel discovers a new solution to Einstein's field equations. It describes a rotating universe. Not just galaxies spinning in space, but the entire cosmos slowly swirling. When you draw the geometry of this rotating universe, something shocking appears. In Godel's universe, there exist closed timelike curves. You can follow a path through spacetime that always moves forward according to your own local clock, never breaking the rules of relativity. Yet when you return, you arrive in your own past. You have not jumped outside of physics. You have obeyed it exactly. The equations born from Einstein's theory and nourished by his cosmological constant allow a universe where time travel, in principle, is real. Einstein is not thrilled. He is uncomfortable with this implication. He worries about paradoxes, about the uncomfortable idea that cause and effect might twist into knots. Yet he cannot deny the mathematics. His wrong turn, that extra term he once regretted, helps make Godel's rotating time travel universe possible. The same flexibility that once held the universe static now lets it spin in ways that bend time back on itself. Later, other physicists push these ideas further. In the late 20th century, researchers like Kip Thorne and his colleagues explore the physics of wormholes. A wormhole is a hypothetical tunnel in spacetime, linking two distant points like a secret shortcut. Under some conditions, if you move one mouth of a wormhole quickly or place it in a strong gravitational field, time dilation can make one end age differently from the other. Connect them again, and you have the skeleton of a time machine. Even when you remove the cosmological constant, general relativity refuses to fully shut the door on time travel. Solutions like Godel's universe, Tipler cylinders, and exotic cosmic string models all hint at ways to fold time. J. Richard Gott, in the 1990s, shows that two infinitely long, rapidly moving cosmic strings could allow closed timelike curves. Most of these scenarios demand impossible ingredients, like infinite cylinders or negative energy. But the important part is this: the theory created to describe gravity naturally spits out geometries where time can loop. Today, when you use GPS on your phone, you casually rely on time dilation corrections predicted by relativity. Satellites orbit high above Earth, where gravity is slightly weaker. Their clocks tick faster than clocks on the ground. Engineers must adjust for both special relativity, because the satellites are moving, and general relativity, because they are higher in the gravitational field. If they ignored Einstein's strange view of time, your location would quickly drift, and the map in your hand would become useless. This is everyday proof that time does not behave the way your intuition suggests. It is already slip-sliding and stretching. You are not building full time machines, but you are living in a world where time can be manipulated, slowed, and skewed. Your technology quietly bends time, just enough to navigate cities. Imagine what future technology might do with the same equations. The experiments that confirm relativity keep stacking up. The Rebka experiment in 1960 measures how light climbing out of Earth's gravity well loses energy, exactly as general relativity predicts. More recently, the Gravity Probe B mission watches tiny gyroscopes drift as Earth curves spacetime around them. In every test, time behaves as Einstein's theory demands. And in every test, your simple picture of time as a uniform ticking clock erodes. You might ask, if the equations allow time travel, why have you not seen clear evidence of visitors from the future? One answer is practical. The exotic matter, or immense energies required to stabilize wormholes or build cosmic string configurations, may be beyond anything your civilization will ever reach. Another answer is logical. Some physicists, like Stephen Hawking, have suggested a chronology protection conjecture, the idea that the laws of physics ultimately prevent time travel to keep paradoxes at bay. Yet even that suggestion is an admission. The equations encourage mischief. Look again at the arc of the story. Einstein builds a new vision of gravity. He bends space and time into a single fabric. He adds the cosmological constant to hold the universe still. Observations show the universe is expanding, and he calls that extra term a blunder. But then, the very flexibility in his equations lets Gödel and others sketch universes where time can fold back. You live now in a cosmos where the expansion is accelerating. Dark energy, which behaves very much like a cosmological constant, dominates the large-scale behavior of space. What Einstein once added by hand now seems to be woven into reality. The wrong turn has circled back into the main road. Your universe appears stranger, more dynamic, and more open to weird geometries than Einstein dared hope or fear. In science fiction, time travel is usually a machine with blinking lights and dramatic levers. In physics, it is quieter. It is a question about the shape spacetime can take and the paths you can walk through that shape. The mathematics that begins with one man's attempt to balance the universe now acts as a catalog of possible worlds. Some of those worlds contain closed timelike curves. Some of them resemble the universe you actually inhabit. And in your daily life, you keep touching the edges of these ideas. Every time you trust GPS, you lean on time dilation. Every time astronomers observe light from a distant galaxy, they peer back in time, because that light has traveled for billions of years to reach you. Every time you hear about gravitational waves, you are hearing about ripples in spacetime, predicted by Einstein's equations and confirmed a century later. Time is not the flat stage you thought it was. It is one of the actors. If you strip away the equations, the names, and the technical words, you are left with something simple and unsettling. Time is not absolute. It changes depending on where you are and how you move. The universe can be arranged, at least in theory, so that time loops. The mistake Einstein regretted becomes part of the language you use to describe the most mysterious forces at work. Your sense of before and after starts to wobble. Yet instead of leaving you lost, this story can give you a new kind of anchor. You begin to see yourself not as a dot sliding along a single line of time, but as a path through a vast four-dimensional landscape. Your choices, your memories, your future possibilities all trace out a curve. The fact that physics toys with loops and shortcuts only highlights how rich that landscape is. You will probably never ride a Gödel time machine, but you are already a traveler through a universe where time is flexible. Tonight, when you check the time on your phone, you will still see glowing numbers that look simple. But now you know that behind them lives a universe where time can slow, twist, and in some solutions even circle back. You know that a wrong turn Einstein once tried to erase helped build the language of modern time travel theory. And you know that those familiar digits on your screen are anything but simple. If you liked this video, do like and subscribe to this channel. Comment below on which scientist would you like to watch next.